In my last video, I made a leg for a quadruped walking robot, but I started to get worried. Was my design good enough that it could run and jump, all the things it deserves to be able to do? In this video, I'm going to enhance almost every part of the design, from mechanics to software. I'll organize this into 4 separate parts. By the end of the video, I'll finish version 2 of the leg, and it should be able to move around. The first step is redesigning the mechanics. For version 1, the motors are inside each joint. Each motor is mounted onto a leg section and directly controls that joint. This had some great benefits. It made the mechanics strong and simple. It also made programming easy because the angle of the motor always matched the angle of the segment. But it also had some downsides that were hard to ignore. Here are my main problems with the last version. First, these motors are heavy. One is heavier than all the 3D printed parts. So having a motor in the knee requires a lot of torque to swing around. I can reduce the inertia by moving the weight of the motors closer to the body. Another issue, the leg had to be wider than the motor. With the motor outside of the joint, we don't have this restriction. I started redesigning the leg. I moved the first motor down to make room to pull the second back a bit. Then, the third could move to the very beginning of the femur and controls the angle of the tibia with a lever. Just as I was finishing this design, I realized I could go further. I could stack all 3 of the motors on top of each other. I can't imagine a design that has less rotational inertia than this. Now, the motors that control the hip and femur are doing what they've always been doing, but the last motor is connected to the tibia through a lever. With the mechanics redesigned, next I'm going to improve the electronics. In retrospect, I'm pretty happy with the parts I used, but there's one thing I want to upgrade. Last time, I used the Mega 2560 controller. When I was still doing research for the first version, but a bit too late to pivot, I came across the Raspberry Pi Pico. Here's all the reasons I'm going to upgrade. It has embedded Wi-Fi and Bluetooth, it's half the size, it has about 16 times the processing power and 8 times the memory, and it's only $7 compared to $20. Also, after checking with an ESP32 I had laying around, I made sure it is possible to use 5-volt servos with a 3-volt controller. With the new controller, I need to redesign the PCB to fit the Pico's footprint. This is where I'll get some help from the sponsor of this video, PCBWay. I'll keep everything for power, to interface with the motors, the NRF radio, and the gyroscope. I can remove the Bluetooth module since it's built into the new controller. Arranging the parts, I'll still put the Pico on the back to save space. Then wire the components together. And the redesigned version 2 of the PCB is finished. This time, I installed the PCBWay plugin for KiCad. This makes it so easy to export the finished PCB. I'll click a button, and immediately my browsers open the PCBWay with all the correct files already uploaded. Then another couple clicks and it's on its way. The last thing I'm going to upgrade before putting it all together is the software. In the last video, I explained inverse kinematics and implemented a simple version. For a refresher, IK is an algorithm where you specify an endpoint for the foot, and it solves the geometry to determine the motor angles. Since I've changed the leg design, I'll have to update the algorithm. I can build on the geometry from the first version. Thankfully, the math for the first 2 motors stays the same, it's just the third motor that's changing. Now the angle of the knee joint depends on both the second and third motors. As the femur moves, it changes the angle of the knee. Using the output of the first version IK algorithm, I already know angles required for the joints. So I just have to solve this irregular pentagon for the angle of the third motor. I know the length of all segments, and the last implementation of IK tells us the angles of 2 of the joints. Using some trigonometry, we can solve the triangles that make up the pentagon to determine the angle of the third motor. In addition to updating the IK, I'm going to make it wireless. The Pico is onboard Wi-Fi, so I'll rewrite the code to use a WebSocket instead of the hardwired serial connection from before. With the software updated, it's time to put it all together. I'll print the parts and clean them up. Two motors are put into the double mount, and 2 layers are added with the backing to hold the bearings. A metal horn is installed into the first part of the femur and placed onto the upper motor. Then the lever also gets a horn and is placed onto the lower motor. Bearings are installed into the 2 sides of the femur and they're assembled. A bearing is also installed into the far side, and the femur is complete. Flipping it over, the lower bar of the femur is attached to the lever, and the opposite side of the lever is installed. Next, the two sides of the tibia are assembled. A bar is placed in the tip of the femur for support, then the two sides of the tibia are joined. Then the end of the lower bar is placed into the tibia. Lastly, constructing the hip joint. A horn is added to the output of the first motor. Then this is placed into the main assembly. Parts to hold the upper bearing are attached to the top, and the mount holds the upper and lower pieces together. With that, version 2 of the leg is assembled. Next, it's time to build the circuit board from PCBWay. I'll score, snap, and install pin headers. Then install the capacitors. There's pin headers for the motor connections and power terminals. You can see version 2 of the PCB is similar to the first one, but definitely a bit smaller. I'll install the power switch and voltage converter. Since we're going wireless this time, it's being powered by a battery. With the motors connected, I can plug in the battery, flip it on, and test out the new implementation of inverse kinematics wirelessly. Seems to be working, so I can move on to the finale, mounting the leg onto a skateboard. I designed and printed some new parts for this. They snap on either side of the board and are lashed together with string. Then I can mount the leg. And the remote-controlled skateboard is ready for testing. It's working just how I expected. I'm much happier with this design, and next time I'll be ready to print some more legs and build a walking robot. Thanks for watching.